Hello everyone and welcome back to another video of the Hidden Quantum Champions. Today we are looking into a company called Vector Atomic Inc. And if you want to learn more about what this company does in the field of quantum sensing and its story all the way up to the acquisition of IONQ, then you are exactly right on today's video because we are diving deeper into Vector Atomic. And before we get into it, as always, get yourself something to drink and get comfortable because this video is not going to be 60 seconds. So it's time to start and dive deeper into this company. And with that, let's get started. We are, as per usual, on the website, and already up here says the disclaimer, IONQ completes acquisition of Vector Atomic, a global leader in advanced quantum sensing and timing. When I created the Hidden Quantum Champions list, which is basically the list that has all of these companies that I'm talking here about on it, and you can find more of those in the Hidden Quantum Champions playlist on this YouTube channel. When I created this list, this acquisition had not yet happened, so there was still a company that was not part of IONQ, and you will see as time goes by that again companies that I have made videos on or that I have made videos about will get acquired by other quantum technology companies because the market is kind of condensing down. So we see the market is growing and all of these kind of startups that are scattered across all the different disciplines, they will be at some point, kind of reorganized into something where, bigger players are just acquiring small companies to add their technology into the existing technology stack to create a broader offering. And also because these larger quantum computing players, they do acquire a lot of funding and they have to spend a lot of money on research, and in order to finance that they need to create products that they can already start selling as of today. And not only quantum computers, but also, for example, quantum sensors like these ones here, so that they can finance, let's say, the long-term goal to get to error-corrected quantum computation. With that, let's quickly look at what Vector Atomics actually used to do, or is still doing, now part of IONQ. If you're looking at it here, it says Quantum Advantage Today. So Vector Atomic products will transform industries from transportation to telecom by harnessing the extreme stability of atoms. Our clocks and sensors deliver performance for tomorrow's world. So they are basically in the business, or they have been in the business, of building, based on atoms, clocks and sensors. So quantum sensors and quantum clocks. And what is a quantum clock? So basically, there is a time reference. So what is actually a second? And this has been redefined over the course of basically human existence. So it started probably with some mechanical watches. Of course, even before that, there was a sun clock, right? As the sun basically shining on some stone that you put in the field, and by that you can measure the time. And then at some point you realize, okay, that changes with the seasons and you have to adjust for that. And then at some day the mechanical clock was invented. I'm not an expert for the whole history of time measurement, but just to say, so there are different stages that this went across. At some point, radioactive decay has been used to define or to measure statistically. Decay has been used to measure times. And at the end, now the atoms are being used to build even more precise clocks and light. And then on the quantum sensors, just to say, basically every sensor that we have, even today's temperature sensors, they're using quantum effects, but the difference between a, let's say, classical sensor and a quantum sensor is the collective property of it. So today's sensors that you can buy in the, let's say, you go to Mauser or to DigiKey or whatnot, like to your platform of choice, you buy a sensor, and that includes, the sensor is using a lot of atoms. It's basically based on silicon, and it uses semiconductor technology to measure, for example, temperature or acceleration or something else. And usually that means you drive a current across, and a current is a lot of electrons that are moving. And the property of those electrons movement is then being, let's say, manipulated by the sensor itself. Now, when you think about quantum sensors, you are basically creating something that is a pure quantum state, like for example a qubit in a quantum computer, and you're exposing that to the environment, and then you're measuring how this quantum system is reacting to that. The system is usually a single quantum system, a single quantum unit, like a single atom and a single photon. It can also be something like a superconducting loop, which on the, let's say, on the equation side of things, a superconductor behaves like a single quantum system, even though it's composed out of many, many atoms. But it can be described with a single wave function, and therefore it basically acts like a single quantum system. And all of these basically, they are being used to then measure the impact from the outside onto the system. Now, why is this interesting? That is because usually those quantum systems, they have an energy quantization, right? That's why they are quantum systems. So they have fixed energy levels, and they can only move in quantities of, like, in fixed steps throughout these levels. So there's no smooth transition or anything. There's just level 1, level 2, level 3. And nature basically operates on those levels. So there's nothing smaller than basically a quantum transition, like, I don't know, an electron going from one orbit to the next one, for example. There are no smaller energies, or these are by definition the smallest energy levels that we see in nature. Of course, you can create smaller energies, but, well, actually at some point it becomes difficult to create smaller energies, more like smaller energy differences. But long story short is, with these sensors you can measure extremely precise because of the fact that they are single quantum systems. And yeah, now there are different ideas of how to use those, and Vector Atomic is using, as the name suggests, atoms to actually create those sensors. Now, here we see different ones, right? So there's this little carousel. We see here an atomic clock. So you see there's like fibers connected to it, and it measures time, right? Free space optical time transfer modules. Then we see here a space-based atomic gyroscope. So gyroscope measures acceleration, and so on and so forth. A gravimeter, so it measures the gravity, the local gravity. And I guess we will learn a little bit more about the applications of those later on. So then it says quantum technology delivered. Quantum physics enables the best measurement devices on the planet. Laboratory atomic clocks are accurate to the second in 50 billion years. Atomic inertial sensors can measure gravity variations of a part in a billion. However, laboratory devices are large, costly, and fragile. Vector Atomic is engineering quantum technology for the real world. Our application-specific quantum solutions have been validated in harsh thermal, dynamic, and radiation environments seen on land, at sea, and in space. So let's decompose that quickly. So the statement is, quantum sensors are very sensitive. However, they are only being used in the labs mostly. And that's because they are big, complicated devices. The idea is for them to make devices that are much smaller, probably, and, more cost effective and less fragile, so more robust, that can actually make it into the field. And by robust, they mean, okay, it can be used in harsh thermal environments. So it can be, you can put it, out in the desert and it will still work. It can be up in the space where there's radiation, like space radiation impinging on it. And it can also move throughout dynamic situations, so with high acceleration, which for sure, if you have, for example, an optical table in a lab, you can definitely not put it into such a scenario, because when everything starts to shake and vibrate, basically things are breaking down, your laser beams are bending around. So it's not so easy to build these devices, I assume. At their core, quantum sensors are built from, and that's now the basic statement here, metal and glass to isolate the atoms, fragile quantum states from the outside world, then lasers and optics prepare, probe, and read out the quantum state, and then electronics and software to orchestrate the precise measurement sequence. Vector Atomic is innovating in all three areas to deliver system-level solutions. And then we see here a couple of images like, I don't know, for example, some ion traps, I guess, and some cavities. Then on the electronic side, we see some PCB that they have designed here, and these little, I'm not sure what it is, maybe like glass traps. And then we see here some control electronics and some possibly probing station, not sure what it is. So, well, that's the different areas of innovation here, right? So where can this actually be used? We see autonomy, for example, here there's a car image, so like self-driving cars, self-driving vehicles, maybe. I guess an accelerometer is very helpful when it comes to that. Communication, radar, cloud, astronomy, and GPS. So I guess, well, probably on all of those also the time plays an important role. I also see there's like a clock symbol down there, so it might also be used for synchronization, where you basically need to, for example, on the GPS, you need to actually relativistically correct the signal that comes from the satellite in order to be able to actually do the positioning in such a precise way. And then, of course, if you have an even more precise clock, you get an even more precise GPS. And now let's dive into the text of the explanation of how that works. So GPS is the pulse of today's economy with more than $1 trillion impact in the US alone. That at its heart, GPS is a global timing network. Satellites carrying atomic clocks broadcast precisely timed pulses that mobile devices can use to pinpoint location and synchronize with communication networks. The timing of these pulses is critical. 3-meter positioning requires signal arrival times accurate to 10 nanoseconds. Tomorrow's technology requires timing accuracy beyond GPS. Centimeter scale autonomous vehicle navigation, ultra-high bandwidth data networks, and precise mapping of the Earth are enabled with timing accuracy of 10 picoseconds. So nano is 10 to the minus 9, and then pico is again orders of magnitude lower. Vector Atomic is building high-performance clocks and synchronization hardware for a picosecond level timing network. Our rack mount optical atomic clocks have been validated versus UTC NIST and at sea. Synchronization has been demonstrated over city scales, 30 kilometers, and can be ultimately extended globally through ground to satellite relays. And that you see here these examples that have been discussed and a couple of images. Then I guess the other one here is on the sensor side, on the gravimeter side. We see it's important for navigation. So you could use, for example, you could build something like a gravity map to navigate below the sea, for example, for submarines. That might be an interesting thing. Climate, of course, might be something, or let's say general development of the Earth, right? So the Earth is basically liquid metal or metal core that has a very thin shell on the outside, which is where we are living. So there's a lot of things happening below the ground, and sometimes we see that these things are happening. For example, when the continental plates are kind of crashing against each other or are rubbing against each other, and that creates earthquakes and tsunamis and stuff like that. So if you would monitor the gravity on a constant basis in certain locations, you might be able to predict these things. You might be able to realize that there are certain changes in how the Earth is behaving, and that might help you to predict happenings, to predict events. Then maritime, I guess, goes in a similar direction as navigation. I don't know. Non-proliferation is, of course, also a topic. Mining and oil and gas are basically going towards using gravity to actually determine what is below the ground and to find areas where potentially, for example, there's a higher density because there's a lot of metal there, and therefore the gravity goes up. So we've discussed about these things previously in another video about a hidden champion that is making these gravimeters as a service. If you haven't seen that video, go check out our playlist because there's also more information in there. Then it says infinitesimal forces, enormous impact. So anomalies in Earth's gravitational field give insight into the world beneath our feet. depletion of aquifers, rising sea levels, oil and mineral reserves, and underground voids all have tiny gravitational signatures. Detecting and mapping these anomalies requires extreme accuracy, often while operating on a mobile platform. Atomic sensors can detect signals that others lose in the noise, capturing infinitesimal accelerations and rotations is the key of navigation when GPS is unavailable, stabilizing the orientation of satellites and exploring the Earth's interior. Vector atomics inertial sensors have the form and function to meet the most challenging operational requirements. Our GAINS gravimeter has operated autonomously at sea, accurately measuring local gravity without the aid of motional stabilization. And then, here you see two examples. So in August, the strapped-on atomic gravimeter generates high-resolution absolute gravimetry maps at sea. Of course, that's interesting, for example, for the military, right? And then the other one here, earlier, atomic gyroscope to be delivered for low Earth orbit demonstration in 2023. Then there's some notion here on the team. So Vector Atomics was founded in 2018 to bring quantum precision to mission-critical applications, including navigation and communications. Our hardware is designed with form, function, and cost for the real world. We are 100% employee-owned with no outside investment or debt. Our team of 65 plus combines industrial, academic, and government experience. Every team member plays an essential role, making Vector Atomic run. No job is too big or too small for any of us. Using ingenuity, can-do attitude, and operational efficiency, we have delivered first-of-kind quantum hardware on time and budget despite the challenging global environment. We are located in Pleasanton, California, in the East Bay Area. And then we see here the team, of course, now part of the IONQ team. And then, our team, our future. So quantum hardware is built for classical technologies. You don't need an advanced degree in quantum physics to make an impact. Our team brings together experts in atomic physics, lasers and optics, electronics, mechanical design, software, firmware, testing, assembly, logistics, and operations. The interdisciplinary nature of our work benefits from diverse ideas and backgrounds. We value strong individual contributions that support overall team and organizational goals. In a small company taking on big challenges, each team member plays a vital role with the opportunity to rapidly expand their skill set. If you like to work on transformational technologies in a fast-paced, team-oriented environment, come join our team. We offer competitive compensation benefits and stock equity to all employees. And I hope that it really paid off for the employees in the acquisition of IONQ. And then down here you see a couple of partners, like for example Harvard University, Caltech. So you see there's like partner or collaborators from the academic side, like also NIST and Honeywell. NIST as a national institution, Honeywell of course as a big corporate player that also has a strong research interest, but you also see NASA, DARPA, and so on and so forth. And that already leads me to the end of, let's say, the company presentation. Of course, this is interesting in terms of what IONQ is doing, because they are also working on a system that is using, let's say, individual atoms. In their case, it's ions, of course. So you have this ion trap technology, but the manipulation of those is very similar. You also use lasers, you use light, you use vacuum technology. So there are a couple of, let's say, similarities. But then, of course, here in the case of Vector Atomic, they're using this for sensors. So they basically make a derivative that is interesting for sensing. So there it's about signal to noise ratio, right? Whereas, and I know that because I worked in a sensor company before, whereas in the other case, it is about, let's say, preparing these states and then using their coherent behavior to run algorithms on it in a very controlled fashion. But basically the fundament, let's say on a physics side, is very similar for these technologies. And then the route to go let's say, into each of those directions is a bit different, as in, sensors you want to optimize, you need to be able to calibrate them, you want to make sure that they have a good signal to noise ratio, you want to make sure that they are stable over time so that they can run in specific environments. And the quantum computers, they are, let's say, much more complex structures than probably a sensor is, but then it's also much more, let's say, long-term to actually get them up and running. And if you're looking at the history of electronics, I mean, getting to today's compute power took quite a while, but sensors have been around for a long time. They were also already there when there were microcontrollers, and even there have been sensors that were, let's say, electromechanical, like think about early microphones, for example, that were recording stuff completely analog, and then, for example, amplifying that into with some transistors into a loudspeaker or something like that. These things, they have existed for a while, and I think it's very similar here in this quantum context. So you have this sensors, you have the computers. At one day, maybe we can even use the quantum computers to take quantum signals from the quantum sensors and then feed them into the quantum computer. And that, by the way, is also very similar to what quantum communication is about, where you basically try to transfer a quantum state that is being produced by one quantum computer, for example, to another one, or of course to use it also for encryption. So you see there's a kind of relationship between all of these technologies, and it's actually also kind of derived from the classical, or let's say the standard electronics that we have as of today. Vector atomic probably plays a role in that. From my point of view, a very valuable company, also from IONQ's point of view, of course. I hope you liked this video. If so, please make sure to give it a thumbs up. If you don't want to see any of these videos of companies that have already been acquired, let me know down in the comments below, then I will not produce those anymore. And as always, I'm looking forward to see you in the next video. Until then, bye bye.